Hello, everyone. In this video, I'm hoping to prove the fixed point theorem. Well, before we get into the proof of the theorem, we should talk about a few things. So we should make sure we understand what contraction mapping is and what Cauchy sequences are. Let's first talk about Cauchy sequences. Suppose you have a sequence in a metric space. All right. So suppose sequence x sub n is a sequence in R, where R is just a metric space. This sequence converges if for any epsilon greater than 0, there exists an integer n, a positive integer. It could be as large as you want, such that rho of x sub n, x sub m, is less than epsilon, where n and m are just indices, which are larger than capital N. All right. So no matter how large you choose this, for any epsilon, no matter how small, this will hold true. If this is true, then x sub n is a Cauchy sequence. It satisfies the Cauchy criterion. So what this means geometrically is, with higher and higher indices, the metric, the distance between the 2 points, gets smaller and smaller. And it makes sense to say that every convergent series is a Cauchy series. Every convergent sequence is a Cauchy sequence. We're not talking about series here. We're talking about sequences. All right, so this is what it means to be Cauchy. Now, if every Cauchy sequence inside of R converges to a point in R, it means that R is complete. Okay? So think about every possible sequence in a metric space. If all of them converge to points in R, in the metric space itself, it means that the metric space is complete. And we care about complete metric spaces for this proof. Okay, one other thing we need to understand is what contraction mapping is. Suppose you have a metric space R, okay, and some mapping F, okay. So F, we're gonna see what it means for F to be a contraction mapping. We define the metric space with distance rho, and if you take basically the distance between any 2 points, okay, in the metric space, this will be greater or equal to, well, we have a term alpha here. This will be greater or equal to the distance between the points after the function is applied to them. Or let me write it this way. The distance between any points after we apply the mapping to it, so x sub n and f of x sub m, this is less or equal to alpha times rho of x sub n and x sub m, where alpha is a positive number less than 1. So what do we see that is happening here? The distances between the points is basically being shrinked here after we apply the function to them. So I mean, contraction here is a semantic. It makes sense semantically because it basically means you're just making it smaller. You're making the distances smaller. So if this is the case, then F is a contraction mapping. Okay. Now we get to the formulation of the fixed point theorem. What this theorem says is, let R rho be a complete metric space. We already saw what complete means. Remember here, complete means every Cauchy sequence converges in the metric space. Also let F be a contraction mapping. So if you assume these two conditions, then there exists a point, there exists a point x in R such that f of x equals x. This point is unique, it's in R, and if you apply the mapping to it, it doesn't change. It gives you the same point. It is a fixed point. This is what the fixed point is. Okay? So before we get into the proof, of course we're going to talk about the proof, but before that, let's try to get a geometric understanding of what this is, or an intuitive understanding. Because it's not very intuitive. Let's take a map, just a normal map. All right, so I'm just going to copy a picture of the map of the United States here. And suppose I do a contraction mapping on it, which means let's say I just make it smaller. I don't rotate, I just make it smaller. All right? So what the fixed point theorem says, if this is a contraction mapping, of course it must be continuous, one-to-one, and on. So it's an isomorphism. So what this contraction mapping, what this theorem says is, wherever I place this smaller map inside the bigger map, there will always be a point that maps exactly the same on both. If we had like a coordinate system that we were describing the points, there will always be a point, a singular point, where the map, where it lands both on both maps. So maybe over here, some point of Minnesota is the same. All right, but not any other point. It's only that specific point. Maybe here, you have the point here of Florida is the same for both. Okay. This is an example of a contraction mapping on the R2 space, two-dimensional Euclidean space. For three-dimensional Euclidean space, you can think about a building with a model. So you have a building and you have a model of it. You put the model inside the building. If it's an exact replica, so it makes it a contraction mapping. So wherever you go around inside the building with the model, you're going to be in a point where your location in the building is exactly that specific location inside the model itself. Okay, so for more on this, for more on like intuitive understanding of what the fixed point theorem says, I would recommend you to check out Vsauce's video on fixed points. I'll leave a link for it in the description. It's a very nice video, which is, I guess, way more accessible to this than this one, because we're gonna get into the mathematical proof now. All right, let's get into that. So let's start with this. Let's say you take an arbitrary point x sub 0 in R. Okay? Apply the contraction mapping to it, and let's say the result is x1. Okay? Apply the mapping to x1, you get x2. Okay? Keep on doing this, and eventually you apply f n many times to x sub 0, and let's call the result x. Okay? So we have a sequence here that converges to a point x. This makes sense because, well, think about this term. This is the same thing as applying f twice to x sub 0. So this is the same thing as f of x sub 0. Because f of x sub 0 is x1. For the same reason, this is true. Okay? Now let's say the sequence here is x sub n. The sequence of these 2 points, are going to investigate what happens with it. Now let's look at rho of x sub n and x sub m, where these are just 2 points in the sequence, the sequence that we talked about just now. And let's say m is greater or equal to n. Okay, so these could be arbitrarily large, doesn't matter. Well, finite. Okay, so what we can do here, we can write these as rho of f applied n many times to x sub 0, comma f applied m many times to x sub 0. Okay? That's what we have here. Well, what can we do with this? Let me get this out of the way. Well, we can remember the inequality for contraction mapping. Where was it? It's over here. Not over here. Before. Over here. Let's apply that here. So we can say this is less or equal to then. Well, we can take an alpha out. Rho of f to the n minus 1 x sub 0. F to the n minus 1 x sub 0. This is not going to help much though. What I want to do, I want to apply this n many times. This will still hold, of course, the inequality. So if you do that, if you take alpha n many times outside, you'll be left with x sub 0 and x sub m minus n. Okay? Because this is greater than n, apply it n many times and you'll be left with x sub n. Well, actually, more explicitly, what we'd be left with is x to the power, well, not power here. This is just to indicate how many times we're applying the function. So this is f minus n of x sub 0. But as we saw earlier, this is the same thing as x with the subscript m minus n. Okay? Here we want to apply at this point, the triangle inequality for this term here. So this is less or equal to, this doesn't change anything. Rho, we can put these in parentheses. Rho of x sub 0, x sub 1 plus rho of x sub 1, x sub m minus n. All right? Close the parentheses. Well, I want to apply the triangle inequality to this term now, which would be rho x sub 1, x sub 2 plus rho x sub 2, x sub m minus n. Right? Well, we'll keep applying this until we reach the following. We're going to apply this as many times as we need. So we added 2 here, plus rho x sub 2 plus x sub 3. Keep on doing this until you get rho x sub m minus n minus 1. This is the term just before x sub m minus n, which is the last term in this specific calculation. Now we're going to have to, our goal here is just to get a common factor, this as a common factor. So we know that this is equal to rho of f applied to 0, well, x sub 0, f applied to x sub 1, right? And this is less or equal to rho, well, we have an alpha here. Again, here we're using the contraction mapping inequality, x sub 0, x sub 1. We get this term too. So now, if I can do this to all of them, we can take that as a common factor. We can do it indeed. Here, this will be rho of f applied twice to x sub 0, f applied twice to x sub 1. This is less or equal to alpha squared. Now f is applied twice, so we take alpha squared. Rho x sub 0, x sub 1. We get the same common term. We apply this to all of them. And what do we get? Let me copy this to the next page and see. We get this whole thing, less or equal to alpha to the power of n. That doesn't change. We take this as a common factor. Rho x sub 0, x sub 1. And what we'll be left with is 1 from this term. This one gives us alpha. This one gives us alpha squared. And this keeps on going until the last alpha, which will be from this specific term, will be to the power of m minus n minus 1. In order to get this term from this one over here, we would have to apply the the contraction mapping inequality m minus n minus 1 times. So we have that power to apply to alpha. All right? This is a sum. We can write that. This is equal to alpha to the power of n rho of x sub 0, x sub 1. And this sum could be written this way. Let's take and this is from I equals to 0 because we start with the 1 over here, to m minus n minus 1 of alpha to the power of I. Okay? Now, I can't calculate this. Not easily. But what we can easily calculate is the geometric series, which is strictly greater than this one by virtue of just having more terms. So this is strictly less than alpha to the power of n rho x sub 0 x sub 1 times alpha, sorry, not times the sum from I equals to 0 to infinity of alpha to the power of I. Of course, this is strictly greater than this term because, again, we're taking infinitely many terms here, where here we only had finite terms. So for sure, this is greater. Okay. Earlier, remember, we said that alpha is less than 1 because it's a contraction mapping. It's contracting. It's shrinking. So this is a convergent series. It's just a convergent geometric series, and it converges to 1 over 1 minus alpha. So this whole thing equals to rho x sub 0 x sub 1 times alpha to the power of n from here divided by 1 minus alpha. Okay? Now this comes from the series. Well, what is going to happen to this term, which is greater than what we started with, which was the distance between x sub n and x sub m, it's gonna get smaller and smaller and smaller as n increases. It actually goes to 0 as n goes to infinity. All right, we're not gonna go to these extremes, but all we need to know is that it's getting smaller and smaller. What is getting smaller and smaller? This term. And when such a thing gets smaller and smaller for units or elements that are in a sequence, it means that this is a Cauchy sequence. If the distances are getting smaller. Makes sense. It means that there exists an epsilon, well, not epsilon, for all epsilon actually, greater than 0, there exists an integer, positive integer, such that the metric between these 2 points is less than epsilon, where n and m are greater than that integer. Okay? What does this mean? This is exactly the definition of a Cauchy sequence. It means these points that we started with, where were they? These points form a Cauchy sequence. Alright? So x, let me write it like this, x sub n is Cauchy. Okay? What does this mean? This means that the limit as x sub n, where n goes to infinity, equals x. It converges to a point in the set. Alright? It's a Cauchy sequence. Well, what can we do here? We can apply the contraction mapping to both sides. We can say that f of the limit of x sub n as n goes to infinity equals to the function applied to the point. Okay? Well, here, let me write it like this now. Let me put this up here. Well, f of x equals to this limit, but f is a continuous mapping. Must be continuous. So we can interchange the limits. Well, not limits. We can interchange the limit with the function. We can say this is the limit as n goes to infinity of the function applied to the point x sub n. Okay? And earlier, whenever we applied the function to a point in the sequence, we just increased the index by 1. So this is the same thing as the limit as n goes to infinity of x sub n plus 1. All right? But n is going to infinity, so this one doesn't really contribute. Infinity plus 1 is infinity. So this is the same thing as the limit as n goes to infinity of x sub n, which, as we saw earlier, is just x. So eventually what we'll have, we had f of x, we have x here, they're all equal. So f of x equals x. Therefore, the fixed point exists. This is exactly what a fixed point is. You apply the mapping to it, it doesn't change. The fixed point exists. But we're not done yet. We want to show that it's unique, right? So in order to prove uniqueness, in most cases, you just assume the contrary and proceed with the proof by contradiction. So assume x and y in R are fixed points which means apply f to x gives you x, apply f to y gives you y. Okay? Here we assume there are two fixed points. Now let's see what would happen on the metric between them. Take the distance between x and y. Okay? Well, since the points are the same as the function applied to them, this is the same thing as rho of f of x, f of y. But we can apply here, what we can apply here is the contraction mapping. We shouldn't forget that f is a contraction mapping. So this is less or equal to alpha times rho of x, y, right? These two terms are in the inequality. I can just ignore this one for now. We can say that rho of xy is less or equal to alpha. Sorry, well, the other way around. No, it's not the other way around. It is less or equal to alpha times rho of xy. Okay? Let's put everything on one side. Subtract this from both sides, and we can take this as a common factor. We can take rho xy as a common factor. And what we'll have left in the parentheses is 1 minus alpha. And this is less or equal to 0 now. Well, okay. So, when can this hold? When can this inequality hold? If this is a positive and this is a negative, or the other way around, or one of them is 0. Well, this is definitely a positive number. It cannot be 0 because alpha is strictly less than 1. And it cannot be negative because alpha is also a positive number. Right? So this is strictly positive. So the only way this inequality that can hold is if the distance between x and y is either negative or 0. But metrics defined on metric spaces cannot be negative. They are positive single-valued functions. This must be 0 then. Rho of xy is 0. But one of the important characteristics of the distance functions on metric spaces is that they only equal 0 if the arguments are the same. This means x must be equal to y, which means they're the same point. If they're the same point, that means there's only one fixed point. Therefore, the fixed point is unique. X is unique. All right? So we proved that the fixed point exists, first of all. Then we proved that it's unique. All right? So that concludes the video. I hope this was helpful, or at least interesting. Thank you for watching, and till next time. Bye-bye.